Now let's implement the Huffman coding in Python. So the first few things which are obvious that I just thought we should write fast before we proceed. The first thing is importing the dependencies. So for importing the dependencies, we need heap queue, which provides priority queue implementation using heaps. You can kindly refer to the video that we did on heaps to get an idea of this. Then the next is counter, which you're getting from the collections library, and this helps us to count the character frequencies in the text that you're going to be receiving. Then in typing, so from typing you are basically getting the type annotations, optional, dict, and tuple. This is going to improve our code readability and maintainability overall. Now, the first major step is creating a node class. And for creating our node class, basically the node object, here we define the building blocks of the Huffman tree. So each node contains a character, it contains a frequency, it contains the left and right references for basically the left and the right child nodes. And we also have this method here, which makes the nodes compressible, basically based on their frequency, and it allows for the heap queue basically to arrange our nodes correctly. Now that that major part is done, let's go to one of the main parts, which is now basically building the Huffman tree. So here we'll create a function and we'll call it building Huffman tree. And this text in our text, the text in our text, and the text is a string. And okay, so this also have a node here. So we're having this function. The first thing we do in our function is we're going to calculate the frequency of the characters in the text. So here we use the counter, which we imported there. So we have should be counter, and this text in our text. Then after getting this, the next thing we need to do is create our heap, and we're going to basically return a node with character and frequency. So we're going to return this for character and frequency in frequency.items. This should be character here. Okay. So the next thing we need to do here is just heapify so that we can maintain the heap property. So we're going to heapify our heap. So it's heap queue.heapify. So we heapify our heap like that basically. So the next thing you're going to do from here is you're going to build a Huffman tree now. So to build a Huffman tree, we just need a while loop here. So we're going to check while the length of our heap, is greater than 1. Well, that is the case. We're going to create basically the first node and then the second node. And remember, from our pseudocode, what we need to do is we need to pick the first two characters with the smallest frequency. So we're going to have node 1. This is the first one that we're assigning, and this will always be on the right. This will be on the left, and the other one on the right. Again, from the pseudocode that we just wrote. So we'll have heap queue dot heap heap pop, and so this is the first element you're getting. Then you're going to have node 2, which is going to be heap queue dot heap pop, and with this we're getting the second one, which is going to be on the right. Then we're going to merge these two. So to merge these two, we just need node. So we're going to pass in none there, and then we just add the frequencies of node 1 and node 2. So node 1 dot frequency plus node 2 dot frequency. So we add those two, or rather we merge them. Then after merging, we're going to basically assign them to the left node and then the right node. So merge dot left, the left of the root. So we have node 1, then merge dot write, going to have node 2. Then finally we're just going to push, so heap q dot heap push. I'm going to push the heap and merge. So we're going to push the heap, everything that is merged basically. So here we're going to finally, after we're done with everything, we're going to have the root node. That is what we return after we finished everything here. So we return the root node. And remember, the root node again is the one that the last one, the last element on the heap is the root node basically, or the last node that is. Then so the next thing we're going to do here, after getting the root of our Huffman tree, we're going to go ahead and generate binary codes. So to generate our binary codes, so we can go ahead and okay, let's see this first. So we built our Huffman tree. Right. So, okay, well, what you can do for now, let's try and test it out first. Let's try and test it out before we proceed any further. So, we're going to need some text. So, let the text be something like hello Huffman. Then we'll try to build the Huffman tree. So, build a Huffman tree, text in the text. I believe it only text. Yeah, we only gave it the text as the parameter there. So what it returns, it's going to be the okay, the roots. Let's just call it heap like that, and then let's print heap for now. So if we run our code, so Python 3, I call this file Huffman.py. So node object at this, I believe we're good for now. Let's go ahead and generate binary codes. So we're going to go ahead and create a function here. We're going to call it generate codes. Okay, and this takes in a number of parameters. First is going to take on the root. So the root is going to be an optional node. Then we need a prefix. So the prefix should be a string. And okay, that is done. Then we're going to need our codes. So the code's going to be optional. So optional, we're going to have a dictionary. Again, the nodes should be a dictionary, should be a string, and okay. So string should be none. Awesome. I think we're good here now. Not really. So, and finally, again, we're returning basically a dictionary. So we need a dictionary here with both the strings. So str. Okay, let's see. Okay, I believe we're good now. So the next thing we're going to do from here, after creating this function, we're going to basically check if codes is none. We just return an empty dictionary. So code should be just an empty dictionary. Okay, like that. Then we check root. So if root is none, we're going to return codes. Okay, return codes. Then if root dot character is not none, we're going to return the codes. So rather we assign the prefix to the code. So root dot character. Then we're going to assign this the prefix. Then from this, basically now just generate. We're going to generate our code. So generate underscore codes. So we're going to have root dot left. Then, so for the left, we are assigning the code, the binary code that we are assigning is 0. There should be prefix plus 0. Okay, and then we're going to also get the one for the right. So generate codes root dot right. Then we're going to have the prefix here. So the right we assign it 1. Okay, and then now we're going to basically return the codes at the end. So return codes. Okay, so with this we generate the binary codes like that, and the prefix codes are stored in the codes dictionary from this. The next thing you need to do is do some Huffman encoding. So to do Huffman encoding, you'll just do it right after here. So let's do Huffman underscore encoding. And this takes in our text, which is a string. And instance tuple. Right. Then now the first thing you need to do is generate a binary tree, because remember we're not generate a binary tree, but get the root from our Huffman tree. So the Huffman tree, remember, it returns the root. So we're just going to build Huffman tree, then it checks in its text. So with that we get the root. Then we need our codes. So for the codes, just call the generate codes function that we just created. It takes in the root that we've gotten from there. Then we'll get the encoded text from here. So the encoded text will be the join. So the encoded text is going to be the codes that we get. The codes that we get for character in the text. So after iterating through all that, then finally we're going to return our encoded text. So we return, okay, the closing parenthesis there. So with this, we basically use the Huffman function to generate the tree. Then we get in the encoded text, which we basically convert input text to a binary string from there. And that's something that we've already done from up here. Now, the last thing we need to do is just decode our, how is it called? We need to decode the text from here now. But I want us to just check, first of all, whether we're getting the encoding. So let's call the Huffman encoding. And then it checks in the text. So it's going to check in this text. And the Huffman encoding returns the encoded text and the root, right? So here, let's just have the encoded text and the tree that it returns. Then when you're printing, I want to print the encoded text. So encoded. So like that. So I'm just trying to check if everything is working up to this point. So if we run our code again. Awesome. So we see this is our encoded, the entire encoded text that we're getting. Now we need to decode this text to get what was the message that was maybe being transferred over network here. So to do that, we need a function to decode everything. So we'll create our function and we can call this function of ours Huffman decoding. And this function takes in the encoded text. So encoded text, and the encoded text, of course, is a string. Then it's going to take in the root. And okay. So the first thing we need, we're going to initialize an empty list here, which is where we're going to have decoded text. So decoded underscore text. It's going to be an empty list. Then we need current the root, that is. So current be our root basically. And what you need to do from here is implement traversal logic for basically traversing the Huffman tree. So you need to traverse the Huffman tree for us to be able to decode everything, since it's the one that contains or rather that's where we defined all our codes and everything. Again, you can refer to the previous two videos to look at how we did that. So to traverse our Huffman tree, we need to move 0 moves to the left child and 1 is to the right child from everything that we defined earlier. So we're going to need to iterate through that. So, and you can just say for bit in the encoded text. So for bit in encoded text, the first thing we need to do is we need to get the current. So the current is going to be current.left. It's going to be current.left if the bit is 0, else the current is going to be basically the right. So if the bit is 0, if the bit is so if the bit is 0, then current is going to be the current.left. That is now the left node. Else it's going to be current dot right, which is now the right node that contains the other one. Then we're going to basically check if the current character, so if current dot character is not none, if it's not none, what we'll do is we're going to basically append the decoded text. So decode the character to the decoded text basically. So just say decoded text dot append. We're going to go ahead and append the current character. It's not none, because that means we've been able to basically decode it. So current dot character, then it's going to be root. Current will be root afterwards. Yeah, so after this, what we'll just need to do is return our decoded text. So we're going to return our decoded text. Should be decoded text like that. Okay, and from this, I believe everything should work. So yeah, once you've reached basically our leaf node, the corresponding character is going to be added to the decoded text which you have here. Then the traversal is going to restart from the root again. Okay, let's go ahead and okay. We've already printed the encoded text. Now let's get the decoded message, and how we do that, we're just going to call the Huffman decoding function that we just created. So Huffman decoding, going to text in the encoded text and the tree, because we're using this tree. To basically decode everything. Then we just print. We're going to print the decoded message. So decoded. Yeah, so we're printing the decoded message. Should be a C here. Awesome. Now if we run this, Also, yeah, so you can see this is the encoded message, and this is once it has been decoded. Again, we just used an example message here. If you can write any other text, the algorithm is going to be able to implement something for all of it. Now that we've seen how everything works so far, this has been a bit lengthy, but we just to check on the complexities of the two, or the complexities rather. So, in terms of complexity, for term complexity, building the tree itself is start with term complexity. So, for term complexity, building the tree takes of n log n. And the reason for this is because we perform heap operations for each character, and we already know term complexities for this. Then this is for building a tree. Then now for encoding and decoding, basically it takes term complexity of O of m, should be lowercase m. So it takes time complexity of O of m, where m is going to be basically the length of the string. So this is for encoding and decoding. That's the time complexity for that. And this other one, this is the time complexity for building the tree. So for building the tree, this is the time complexity for that. And the next thing is for in terms of space complexity. For space complexity, the heap is going to, okay, just write out the thing here. So complexity. So for space complexity, the heap takes a space of O of m. O of m, not O of m, but rather O of n, where n is the number of unique characters. We've already used m there. Then we have, in terms of the tree takes a space complexity of O of n. Again, this is basically for storing our nodes, and again, depends on the number of unique characters. Then now for the encoded text, the encoded text, this is the one that now takes this is the one that takes O of m. This one that takes O of m, and this is basically because it depends on the size of the input, and typically is O of m. So this is the time and space complexity for both. But just in conclusion, we've walked through Huffman coding. So building the Huffman tree that we have using a priority queue. We've gone to generating binary codes through using recursive traversal here. Then we've gone to encoding and decoding the text using Huffman coding. But yeah, Huffman coding, from what we've seen, is that it is used widely in compression algorithms. So, like we saw from zip to JPEG, and it's used to reduce the storage space without losing information. And we've seen, we can refer to the first video that we did on Huffman coding, on how it reduces the size from whatever original size was to the other size that after basically doing the compression. And yeah, that is basically it on Huffman coding. If there are any questions on something that probably is not clear, or you want something to be a bit more clarified, kindly do ask so that I can find a way to help you out. Cheers.